Hello guys, let us once again be back at real analysis. We will be dealing with the sequences of real numbers. Up till now, we dealt with the sequences of real numbers which are convergent and converging to certain limit. In that case, we have seen the operations on convergent sequences. If two sequences converge to their own limits, the sum of the sequences also converges to the sum of the limits. Same with the difference. If the sequence S converges to L, sequence T converges to M, then S minus L converges to L minus M. Same way we have shown that S square converges to L square. The sequence of squares of the respective terms converges to the square of the limit. Even if we have any real number k, then k into s means each term multiplied by k. Such kind of sequence also converges to k times the limit L. One more thing we have seen, product Sn into Tn. This kind of sequence also converges to the product of the limits L into M. And one more thing we have shown last time, that is the reciprocal of a sequence converges to the reciprocal of the limit provided the limit is non-zero limit, in that case only. With the help of the same statement, I would like to go to focus on the quotient of the sequences. If Sn n running from 1 to infinity and Tn n running from 1 to infinity are sequences of real numbers, and if the limit of Sn is L and limit of Tn is M, where M is non-zero, then the limit of the quotient sequence Sn upon Tn will also be on the same lines. It will be L upon M. Now to achieve this, what we are doing, we are taking Sn upon Tn as, we are having Sn upon Tn, and instead of dealing with it as a quotient, we are taking the product of two sequences, because we have already dealt with the product and even the reciprocal. So let us take the reciprocal. We better know that the reciprocal sequence converges to the reciprocal of the limit, and it is already known that Sn is going to L, so Sn will converge to L, and 1 by Tn converges to 1 by M, meaning thereby this product Sn into 1 by Tn will converge to the product L into 1 by M, which after all means L upon M. So ultimately we come to the result that the quotient Sn upon Tn converges to L upon M. So it's very simple and very usual, very expected one. Then as usual, we have seen the convergence of given sequences. If suppose anybody asks us to show that the limit of 2n upon n plus 4 root n is 2. So up till now, what we used to do was we used to take n common, get it cancelled and deal with the sequences. Same kind of thing here we can go. What we do is we get the largest power of n common from the numerator as well as the denominator. get it cancelled, and just talk about the separate sequences that you are getting in the numerator and in the denominator as the reciprocal, and just talk of it as product of the terms like this. It assures the claim of the limit. So let us see over here. We are given to prove limit n tends to infinity 3n square minus 6n upon 5n square plus 4 to be 3 by 5. So what do? First we are dealing with the terms. So 3n square minus 6n upon 5n square plus 4. We have taken n square common. Once we take n square common, from the numerator we have n square, from the denominator also we are having n square. So that n square is going to get cancelled. And inside we are left with 3 minus 6 over n upon 5 plus 4 over n square. Now we know 3 is a constant. We should not bother about it. We are just thinking of what happens to 6 by n, and as we know the limit of 1 by n is 0, so the limit of 6 by n will be 6 times 0, meaning 0 there. So this way we are going to handle the sequences. So we do have 3n square minus 6n, and upon we do have 5n square plus 4. So what we have done here, we have taken this n square out. As we stated, from the numerator we got 3 minus 6 over n. And in the denominator we saw it was n square, and inside we have 5 plus 4 by n square. So the same fact we used to utilize up till now. And now you are watching this n square is off, and we have just to think of what happens to 3 minus 6 by n and 5 plus 4 by n square. So same thing that we used to utilize up till now, we will be handling. Okay. So if I apply limit as n tends to infinity to constant sequence 3, it will be certainly 3 back. And if I apply it to 6 over n, we know it is 6 times 1 by n. It will be 6 times 1 by n. So ultimately, what do we get? 3 minus 6 times 1 over n. Only we wanted to emphasize this, and limit of 1 over n is going to 0. So what we will get? We will get 6 times 0. This is what is explained over here. So this comes out to be 3. Same way in the denominator you will observe this limit n tends to infinity (5 plus 4 by n square). We will read it as 4 times 1 over n square. And now you apply the limit, 5 being constant term, constant sequence, its limit is the same. And this is surely going to be 4 times, because 4 multiple, and 1 by n square goes to 0, it is converging to 0, so our ultimate answer is going to be 5. And the reciprocals or the quotient thing we are going to apply. So this is going to be 3 by 5, which was very usual. So hope nothing to explain over here. Now going back, let us deal with the operations on divergent sequences. So let us be back here. So they have given a list of questions to be proven. I hope it's quite easy to handle. Here in this case, in the first case, we observe it is 2n cube plus 5n. In the denominator we are having 4n cube plus n square. So take n cube common, you will be left with 2 plus 5 upon n square. In the denominator it is 4 common, n cube common, you are left with 4 plus n 1 by n. So ultimately the thing will go to 2 by 4, meaning half. So I hope you can solve this. And going here also, it's quite simple. You can observe let us read it aloud. What is going to happen? N square is in the numerator, so let it stand, and in the denominator, if I take n square common, what I'll be left inside with? From the bracket, because bracket is squared, if I take n out, it becomes n square, that we all know. So in this place it will remain 1, and here it will be 7 over n. Feel it is quite simple. And if we want it at all to be out from the total denominator, then I should bracket it over here, and I should call it as minus 6 over n square. So what we observe is n square is common throughout from the denominator and gets cancelled. What we are left with? The numerator is purely constant 1, and in the denominator, after applying the limit, what we will be left with is 1 minus a 0, it's square, and minus a 0. So obviously the answer is going to be 1. I hope it is a simple one. Rest we have already seen. This kind of thing we have already seen. Alright. So now I would like to proceed for, as I said, divergent sequences. So we are talking about the operations on divergent sequences. So what is going to happen? If Sn and Tn both are sequences of real numbers that diverge to infinity, so same kind of sequences we are saying. Sn diverges to infinity, Tn diverges to infinity. What will happen to their sum? Obviously the sum will also diverge to infinity. If we talk about their product will also diverge to infinity. Here diverging to infinity kind of concept we need to explain in detail. So let us see what is the actual concept. See here, Sn we want to say Sn is divergent. What it means? Divergent means the numbers will expand and we will not be able to control the numbers, will not be able to get a point, a real number where the terms are gathering. The terms are splitting here. What I mean by this, so if suppose I take a sequence which is quite familiar to us, that of n, or let us go to n square, will do. What are the terms with us? Terms of n square. First term will be 1 square, 1. Second term will be 2 square, meaning 4. Third term is going to be 9. Fourth term will be 4 square, 16, and so on. So what we observe here, this kind of terms, they will never gather anywhere. So if I give you any real number m and ask you about the terms, suppose in this case I take m equal to 70, something like this. So if I talk about 70, 9 square is surely greater than 70. So if I take n equal to, capital N equal to 9, what do I observe? All terms after this n means 9, or equal to n, this n square is surely greater than this particular capital M. What is this n square? N square meaning Sn, term of the sequence, Sn. Sn is going larger than this particular M. What M you have taken here? 70. If you ask me another number, we can still go with it. If you want M equal to, suppose, 150, what you can say? I want terms whose value is greater than 150. We know the square numbers. 11 square is 121. 12 square is 144. So they don't obey this. 13 square is 169. Yes, from 13 on. Meaning if I take n greater than 13 or equal to 13, I find Sn, meaning n square, greater than this fixed m, this particular m, and I can say for all. What is the statement I have got? Sn equal to n square greater than m for all n greater than equal to 13. So what is the concept of diverging to infinity? So you give any real number m, for that real number I can get the term number n. So after crossing this n, all values of Sn are greater than this particular m that we are talking. So this is the meaning of divergent sequence. Means the terms are expanding, the terms are going ahead, the terms are not under control. This is the meaning of divergent sequences. So if anybody wants to ask any concept, you can write in the chat box. Go in the chat box. Is this fine? So I would like to go with the poll. The sequence curly bracket, round bracket, 2n plus 3 bracket close divided by n raised to 4. So options are converges to 2, converges to 3, converges to 0, diverges to infinity. Question is with you. Yes, go ahead. Go with the poll. We have sequence 2n plus 3 over n raised to 4. So will this sequence converge or diverge? So I end the poll and let us see what is the answer. Yes, I end the poll, and I would like to go with the question. What it asks us is, if at all you are having 2n plus 3 upon n raised to 4, so it looks like this, n raised to 4, and very obvious, you can take only one n common from the numerator and n will get cancelled with this result, is it? So you can observe there is n cube in the denominator, 2 plus 3 by n is present in the numerator, and by this quotient kind of thing, what you are left in the numerator with is 2 and multiplied by a 0. I can read this aloud as what? 2 plus 3 by n, damn sure, and multiplied by 1 over n cube. 1 over n cube goes to 0, as you all know. So the result will be a 0. The sequence will be converging to 0. Hope the concept is clear. This particular kind of sequence converges to 0. Now, if suppose you are given a sequence like exactly reciprocal of the same, let us deal with exactly the reciprocal. N raised to 4 you are having in the numerator, n raised to 4 you are having, and suppose denominator contains 2n plus 3. So in that case, what is going to happen? You will take n common from the denominator and you are left with 2 plus 3 by n, as you are watching in the upper part, and this is n raised to 4 means n into n cube. I can say I can get this n cancelled and I am just left with n cube upon this particular. Now what you observe, just go with the terms, first term, second term, third term. I think the result is quite clear to you. If I put n equal to 1, what do I get? 1 over 5, is it? 1 over 5 means 0.2 you are having. Hope so. Second term is going to be 2 raised to 4, meaning 16 upon 2 2s are 4 plus 3, 7. 16 by 7. So you'll have 7 2s are 14 plus 2 is left. So 2.2 something approximately we are writing. What happens next? If you go to 3 raised to 4 takes you to 81, and upon 3 2s are 6 plus 3 is 9. The value jumps to 27 directly. So you can see the values are rising. This is 0.2, this increased straight away to 2.2, and now it is jumping straight away to 27. Thus values are going on rapidly increasing. So such kind of sequences we call as what? Divergent sequences. So this sequence is diverging to infinity. All the terms are positive as you are watching. So it goes to plus infinity. So let us go back with our concept. We wanted to talk about the divergence. Okay, so let us go back with the same kind of statement. If suppose you are having two sequences, both are diverging, so obviously the terms will go on. So you will be able to find out the value after which the terms are going on increasing. So in this case, basically, let's have sequence Sn is there. and sequence Tn is there, both are divergent sequences, means you will be able to find out some real numbers after which the spread cannot be controlled. Meaning for some capital M1 we will have N1, so that Sn will be larger than M1 for all n greater or equal N1, and for this Tn let us have M2, and for this M2 we will be able to find out N2 such that the terms Tn will be greater than this M2 for all n greater than or equal to N2. So this is the meaning of diverging to infinity. So it's obvious if I add these inequalities, and I take the maximum of this, certainly both the inequalities can be merged. If I say capital N is the maximum out of this N1 and N2, so what do you observe? All n's which are greater than the maximum will satisfy both the inequalities. So if you add Sn plus Tn, certainly I would like to go with this color, Sn plus Tn, what will happen? This will be certainly greater than M1 plus M2. What we want is the terms should be larger than a fixed number. We cannot control it, and this is true for all n's which are greater than or at the most equal to the maximum of N1 and N2. Same kind of thing you'll observe if you take product, because product of inequalities, greater side if you multiply to the greater side will always remain greater. So Sn into Tn obviously will be greater than M1 into M2, but sure, and this product sequence will also be divergent. It will diverge to infinity. This is what we mean over here. So this was the case when both the sequences were diverging to infinity. But this may happen in our next theorem we are watching, that Sn diverges to infinity whereas Tn is bounded sequence. In this case we were watching Sn and Tn both diverging to infinity. But if Sn diverges to infinity and Tn bounded, in that case what will happen? So in that case Sn plus Tn will diverge to infinity. In that case Sn plus Tn will diverge to infinity. So let us prove it, how it happens. So very immediately you can see Tn is bounded, means small tn will be less than or equal to something, some fixed real number. There will be some upper bound. What we mean by bounded? Concept of convergent is quite different than boundedness. So let us see what is meant by bounded. So we better know. If we talk about the sequence of 1 over n, so how are the terms? Mod of 1 by n is always less than or equal to 1. Maximum value is 1. But so actually this sequence converges to 0, we all know, and every convergent sequence is bounded, this also we know. You may deal with the sequence of minus 1 raised to n. So what is this sequence? It contains the terms like minus 1, comma 1. So what you are watching, if you put n equal to 1, this is minus 1. N is 2, it will turn plus. N is 3, minus 1. N is 4, plus 1, and so on. So we can see the sequence is bounded. All the values are smaller than 1. Okay. So not only all the values, we should say modulus of the values, because I may have minus n kind of sequence. I hope it is readable. If I handle minus n kind of sequence, certainly this sequence will be minus 1, comma minus 2, comma minus 3, and so on. So what I can say, all the terms are smaller than 0. So if all the terms are smaller than 0, does it mean that the sequence is bounded? No. Why? Because the terms are going to minus infinity. This sequence is not a bounded sequence. So what I should assure the absolute value should be smaller than some fixed number. In this case, if I take the absolute value, the values are going to plus infinity. So they cannot be smaller than any positive number. So this is what we mean. So we need to talk about the absolute values. So in this case, the absolute value is only 1. So this sequence is a bounded sequence. Alright. Going back. So we were talking about sequence that diverges to infinity, and another sequence that is bounded. So in that case, what is going to happen? Let us see. Sn is diverging to infinity. Sn is diverging to infinity means Sn terms become greater than some given number m when we cross certain term. So that certain term we are calling as n, and we are given sequence Tn, which is a bounded sequence. Means mod of Tn will be smaller than some positive real number. So in this case, we watch the number is q here. They have taken q. So mod Tn is less than q. In this case, you can find q is a positive real number, and this happens for all n belonging to I, not for certain. This is for all natural numbers. So what this means, if at all I am handling this, mod Tn is less than q. Alright, what we want to talk about? We want to talk about whether it diverges or converges. So what we will do is, we will take Sn plus Tn, sequence Sn plus Tn. We want to talk about Sn plus Tn is diverging to infinity. So damn sure this Tn will be either, we know the property of real numbers, minus mod a is less than or equal to a, which is less than or equal to mod a. Means what? Whatever a real number we are handling that lies between negative of its own absolute value and positive of its own absolute value. If a is negative, it will be exactly equal to minus mod a, but it is already smaller than plus mod a. And reverse way, if we think, if a is positive, a will be itself plus mod a. So in that case, it is greater than minus of mod a. So the value of a always lies between its negative of its own absolute value and positive of its own absolute value. So this fact we are going to make use of. So mod Tn is less than Q, we all know, but Tn itself is greater than minus mod Tn. This fact we will be using. So what will happen? This particular sum will be greater than or at the most equal to. We are not touching Sn is as it is. This fact we are making use of only for Tn. So because we are changing for Tn, let us use another color for Tn. So this will be minus mod Tn. Hope it is clear. This fact I have made use of. Okay. And certainly this is for all n's I am using. This is for all n. For all n. In I. For all n in I. Okay. Then this inequality we have to make use of. If I apply this result for this inequality, what is going to happen? If I multiply by minus 1 over here, it will be minus of mod Tn. Inequality will reverse and this will be minus Q for certain. So this value is going to be greater than minus Q. Yes. So certainly I can write here greater than, and here I can use the symbol minus Q. And for Sn, I know Sn is greater than m, but it happens only after crossing this n. So let me use this Sn greater than m, so this will be m. So what is the result we have got? I have to apply here for all n greater equal capital N. Because this particular was for all n's and m is only after crossing n. So if I combine both the results, it will be after crossing this particular value. So what we have got? Sn plus Tn is greater than m minus Q. So if I want at all to get rid of this minus and all, what we will do is we will go slightly up. And let us say we'll go up, and what we'll do is we'll say Sn is greater than m plus Q. This is fine. So in this place it becomes, so let me clear this. Yes. And instead I can say this value is already greater than m plus Q, and we have attached minus Q here. So ultimately where we are reaching? M plus Q minus Q, so we reach to m. So what should I now read? Sn plus Tn is greater than m for all n greater or equal n. So what we have shown, Sn plus Tn is diverging to infinity. I would like to reuse the fact, I would like to reshuffle it. So I go back, and in simple language let us deal with the same fact. We are given sequence Sn which is diverging to infinity. Diverging to infinity means after crossing certain n, what we observe, the terms Sn become greater than a fixed real number. Which real number you want accordingly. Last time we had dealt with some numbers, as you saw, after 70 or after 150, likewise. So in this case what we are doing, we are taking the number as per our wish, that is m plus q. Why? You observed already. So what we are saying, Sn is greater than m plus q for all n greater equal n. Okay. Now another thing is given to us, this Tn. How is this Tn sequence? It is bounded. So bounded by some number. Same q we are utilizing here. So Tn is bounded means the absolute values of the terms become smaller than this particular q. At the most equal is allowed, and this is true for all n, for all natural numbers. We denote the set of natural numbers here by I. Yes. Now I want to combine both the results. To combine, we have taken the help of this mod Tn. We know this is going to be minus mod Tn. We multiplied by minus 1 greater equal q. Sorry, this is minus q. And this will also happen for all n belonging to I. That's natural. What fact we have made use of? We have made use of Tn is always greater or equal negative of its own absolute value. So Tn will always be greater than minus of mod Tn. So let us combine the result. We wanted Sn plus Tn. So we said this is greater than or equal to Sn minus mod Tn. So we know better that Sn is greater than this fixed value. Let us use it. So what we are saying, this is greater than m plus q and we are adding this result for minus mod Tn. Minus mod Tn is already greater than minus q. So this will be minus q. Greater than type of inequalities we are adding together. So we reached over here and this is nothing but m. But this is for all natural numbers and this is for certain infinite number of natural numbers. So if I combine the result, what I should say, for all n greater than or equal to capital N. So we have shown that the sum of the sequences is diverging because it is going beyond, it is becoming greater than a fixed value. So this goes to infinity. Alright. Now let us come back here and let us talk about the corollary. So that will end the operations on divergent sequences. Here Sn diverges to infinity but Tn is convergent. So we handled, up till now we have handled two cases. Sn and Tn both were diverging to infinity, so sum diverged to infinity. Second case, Sn diverged to infinity but Tn was bounded. And now as its corollary we are handling Sn diverges to infinity but Tn is convergent. So what will happen to the sum? Sum will also diverge to infinity. How? So as we are saying, same kind of case here. Sn diverges to infinity, but Tn is convergent. So Sn diverges to infinity, but Tn converges. If Tn converges to L, will mean mod Tn is less than or equal to some fixed value. So obviously we will be dealing with some Q again, and going with the same kind of result, we can show that Sn plus Tn is greater than or equal to this M, meaning thereby this Sn plus Tn is divergent. So that's all for the operations on divergent sequences. We have only dealt with Sn diverges to infinity and its combination with, first, a divergent sequence Tn, secondly we dealt with bounded sequence Tn, and lastly we dealt with a convergent sequence Tm. In all the cases, Sn plus Tn diverges to infinity. Alright. Now in exercises 2.8 you can see they have given something. Sn diverges to infinity, Tn is diverging to minus infinity, and they are asking you to give example of Sn plus Tn going to diverging to infinity. So can you give an example? Sn diverges to infinity, Tn diverges to minus infinity, still Sn plus Tn is going to infinity. Yes, Sn diverges to infinity, Tn diverges to minus infinity, still Sn plus Tn diverges to infinity. So here are two cases we have to deal with. Suppose let us have Sn as n square, and we know n square diverges to infinity. Let us have Tn as minus n, and we can see it goes to minus infinity. And now if I add Sn and Tn, Sn plus Tn, what will happen? This will be certainly n square minus n. If I take n common, inside I am left with n minus 1. And where does it go? Where does it go? It goes to plus infinity. It goes to plus infinity. You can watch it. If you go with the terms, 1 square minus 1 is a 0. 2 square minus 2, 4 minus 2 is a 2. 3 square, 9 minus 3 is a 6. 4 square, 16 minus 4. And so on. So you watch, the terms are going to plus infinity. So you can have such examples where Sn diverges to plus infinity, Tn diverges to minus infinity, still the sum is diverging to plus infinity. This kind of examples you can construct. There was another question. Sn diverges to infinity, Tn also diverges to infinity, but Sn minus Tn converges. You are talking about subtraction. You have proven that addition of divergent sequences also diverges to infinity. If they are of both same kind of sequences, their sum also diverges to infinity. But if you talk about their difference, you cannot guarantee. So let us deal with such sequence. We are trying to solve this particular. Sn diverges to infinity, Tn diverges to infinity, but Sn minus Tn is converging to 7. So let us deal with this. Suppose I have sequence Sn we have sequence Sn as n plus 7. So obviously it diverges to infinity. And let us have Tn equal to n only. So I know it also diverges to infinity. But if I deal with Sn minus Tn, what is the term? N plus 7 and minus n. So certainly this is a constant sequence 7 which converges to 7. So difference we cannot guarantee. If the sequences are going to infinity, the difference might not be divergent, it may turn convergent. So we have constructed this example. You can find out another example also. So hope this is quite simple to construct such kind of examples. So at this moment I would like once again to go with a poll. The sum of convergent sequences is convergent. Yes or no? So he ended the poll and majority is correct actually. In mathematics, majority has no value, correctness is correctness, but here we have found that majority of the people are correct. Sum of convergent sequences is always convergent. We have shown this. Convergent talks about bounded sequences, convergent sequence is ultimately a bounded sequence, and the values, when they are in control, there is no question as such. We have already shown S and T, if they are convergent sequences, if they converge to L and M respectively, then the sum of the sequences S plus T also converges to L plus M. I would like to go with another poll. If capital S is convergent and capital T is oscillating, then S plus T converges is the question is asking about if one sequence is convergent and the other is oscillating, what will happen to S plus T? Okay, end the poll and let us see what is the answer. Let us handle Sn equal to, we want convergent sequence, so let us take it to be 1 by n, and we know it goes to 0. Let us have another sequence Tn, and we know Tn we want oscillating. This will be -1, +1, -1, and so on. We know this. So in this case, Sn plus Tn, what will be the terms? Sn plus Tn. Sn plus Tn. If I go with even terms, S2n, T2n, in that case this goes to 0 plus 1, it will go to 1. If I go with odd terms, S2n minus 1 plus T2n minus 1. So what do I observe here? This will go with 0 minus 1, and the answer is going to be -1. So neither it is going to +1 nor it is going to -1 constantly. Alternately it is going to +1 and -1. Means the sequence is divergent sequence. It cannot converge. It cannot converge. Even we may have diverging, oscillating infinitely kind of sequence, because there we haven't mentioned. So in this case, if suppose I have into n, then what I observe, this is -1 plus 2, this will be -3 plus 4, and so on. So that kind of terms will be, actually this is going to be 2n. 2n means it will not converge. It will not converge. It will go to plus infinity. And in this case, it is going to be 0 minus 2n minus 1. So it will surely go to minus infinity. So in that case also it diverges. It will not converge. It will not converge. Okay. So this is very difficult to decide when one is convergent and the other is oscillating. So in that case we can't determine properly, so can't say is the correct answer. Hope the operations on divergent sequences was quite fruitful to you. So with this, let us stop. Bye.